It's a great pleasure to have the one and only mathematical magician, Persi Diaconis, who will talk about how to get ruined gambling. Go ahead.
Well, this is the opposite. This is how to make the only way to make money gambling, which is to prove theorems and write papers, because the other ways aren't so easy. Hi, everybody, and this is a nice topic, and I'm going to start a little bit from the beginning, which I hope we're okay, and anybody's welcome to ask ask questions at any time. Let's see if I do share. That should show. So let's see. So this is a report of joint work with Stew Ethier, whose name I seem to have misspelled, and Huston-Edwards, and Laurent Saloff-Coste. Let me start with the big picture, and then I'll specialize to classical gambler's rune, and then I'll come back at the end and say some things about the big picture. So the big picture is the following. You have a finite set X. There it is, X. And you have a Markov chain on X. That means, for me, a matrix, KXY, where the entries are bigger than 0 and the row X sums to 1, summing in Y. And such a matrix specifies a Markov chain. From X, you look in row X of the matrix, and you pick a point Y with probability proportional to K of XY. And then you're at Y, and you look at row Y, and then you pick a point from K of YZ, and so forth. You just walk around according to the Markov chain. And there are no tricky technical things. You may as well assume all of our Markov chains go every place and so forth. So you have a Markov chain, some way of marching around. And then an additional object is a set B in the state space, some subset. And the problem is the following. You start someplace inside B, and you start running your Markov chain. And when you get outside of B, assuming that happens, when you get outside of B, you die. That's it. You stop, or the process stops, more colorfully. And that's a so-called absorbing Markov chain. And let's see, we need to be able to scroll down. There are several natural questions, but two at the moment. One natural question is, how long does it take until you die? How long do you live? And in symbols, capital T is the random time until you exit. And what's the chance that starting at X naught, that you live for at least time T, and any kind of question you want to ask about this distribution, but how long to exit? And a second natural question is, when you exit, where are you? And the way that looks in symbols is, what's the chance, given that you start at X naught, that when you exit, you hit Y, some point outside? And an important thing for me, I like finite things and like to keep track of things and take limits as late as I can. How do the answers to these questions depend on where you start? Obviously, if you start near the boundary, you'll exit fast, but being more quantitative about that, and how does where you exit, how does that depend on where you start? So those are the big picture questions. And the most classical special case of that is ordinary gambler's rune with two gamblers, and their X could be taken as a space 0, 1 up to n. The first n integers, just a usual path graph, and the nearest neighbor random walk on X. You go left or right with probability 1/2, and if you want to worry about it, if you hit 0, you stay there half the time and go back right, and same at the other side. The set B can be taken to be 1 up to n minus 1. So the boundary, the points outside of B are 0 and n. And then you stop when you hit 0 or n. And the way this is usually said is there are two gamblers, and the first one has X naught dollars, and the second has n minus X naught dollars, and they flip a fair coin, or they play a game at which they're equally skilled, and which you win or lose a point with probability a half, and then you stop when one of them goes broke. And the answers to our two questions are classical theorems from De Moivre, from Laplace, and those times. The average time until you stop, the expected first stopping time, is given by this product, x naught times n plus 1 minus x naught. And so, if that's one fact. And what's the chance you stop if you start at x naught, that the right-hand guy wins all the money? Well, it's that you stop at n, it's x naught over n plus 1, and the chance that you hit 0 first is 1 minus that. So it's a little surprising. So if I had $1 and Doran had n minus $99, and we're flipping a fair coin, so it's unlikely that I'll win, that I'll wipe Doran out, but it's not so unlikely. It's not exponentially unlikely. The chance that I win the $100 altogether is 1 over 100. So it's a little surprising. But okay, that's just to get us started. And a problem which still has challenges is Gambler's Rune with 3 gamblers, and there are many models for this, and I'm going to talk about several of them at the end, but the one that I'm going to talk about now was sold to me by a great poker player named Chris Ferguson, also known as Jesus Ferguson, and he won the World Series of Poker 2 or 3 times, and he's no fool. He's got a PhD in computer science, and his dad's a famous statistician, Tom Ferguson. And Chris got in touch and said, nobody knows the answer to this problem. And the problem is this, and he felt as if it was important for tournament poker. We have 3 gamblers. One has A, one has B, one has C. And this version, you pick a pair of gamblers at random, all 3 possible pairs being equally likely. And then you flip a fair coin, and if it comes up heads, you transfer $1 one way, and if it comes up tails, you transfer $1 the other way, and that's a well-specified game. And eventually, because everything's finite and you're wiggling around at random, and I'll call the time it takes T1, one gambler is eliminated, and so the 2 gamblers have the money between them, and then they play ordinary Gambler's Rune until all the money is gone, and all the money is won by one player, and T2 is the time the game ends. So that is one version of Gambler's Rune. You could make it with K players. We'll do it with 3 right now, and that was studied fairly classically by a guy named Bachelier, who was a marvelous mathematician, and he wrote a book came out in 1912. And 2 of the things he proved in his book, which have been rediscovered by modern authors, 2 different proofs, is the time until you hit the first boundary, the time until the first gambler is eliminated, has this nice formula, 3ABC divided by A+B + C. And just to make numbers, if each of 3 players had 100, this thing turns out to be 10,000. So it takes a long time if you start in the middle. And if 2 of us have $1 and Doran has $298, the chance that the chance that the game ends, probably Doran's going to win, sure. The big player wins, the guy with the most money, and the time is fast. If you're near the boundary, the game ends in 3 steps or something like that. T2, which is the time, T1 plus the time it takes the remaining 2 guys or ladies, whatever, to finish the game. Also, there's a nice formula for it. AB plus AC plus BC. That's the time it takes the whole game to finish, and that is 30,000 if you start in the middle, 100, 100, 100, and it's around 600 if you start in the corner, 298. That's the start of getting our hands on the hitting time. This is just the mean hitting time, and you can ask for the variance and the distribution, and I'll talk a little more about that. But that's the first of our questions. Say something about the first hitting time. The where you hit is harder, and it's still a little bit delicate, and I'll talk about it more carefully in a second. But a classical theorem, also proved by Bachelier, is that the chance that the player who originally had $A wins is proportional to how much he had, A over A plus B plus C, and the same for the second and the third. The chance that the first player winds up with all the money is proportional to how much they started with. So that's the first of our problems. Say something about the hitting time, and let me now pose something that I find surprising, and hope somebody will have something to say about it. So now consider the case in which, Neil, Sloan, and I each have $1, and Doran has N minus $2. And sorry, let me go back. With okay. Neil and I each have $1, and Doran has N minus $2. So surely the game is going to end very fast. What's the chance that Doran is eliminated first? Sorry, Doran, but it's a rare event, but what's the chance? Well, you might think, so here's a heuristic. You might think, well, Neil and I each have $1. That's like one guy with $2, and Doran has, N dollars. And it must be the same as ordinary gambler's rune, and the chance is probably that the big guy gets eliminated first is rare. Maybe you might think it's constant over N. That's one heuristic. There's a second heuristic that's very widely used in poker tournaments. It's called the ICM. It's the way that professional poker players settle tournaments. Everybody thinks they're gambling for millions of dollars. In fact, the night before they say, we don't really want to gamble for $10 million. Suppose we split the pot and only gamble for $1 million of what's left. How should we split the pot? It should have to do with how much each of us has now. And they use something called the iterated card model, ICM. And in this problem, what's the chance that the big player is eliminated first? The ICM predicts that the chance the big player is eliminated first is constant over N squared. And math says something else. Math says the answer is constant over N cubed. And so that's a theorem, actually. And now we know the constant, and it's this charming thing. It's 0.5. As Doran would say, it's 0.5597, and he would probably go on, and we could too, 50 decimal places. But even better, it's square root of pi over 3 square root of 3, gamma to the third over gamma to the 5/6 cubed. So we know what C is in any sense you want to see it. That's a theorem, and I'll explain. And I have no idea where this 3 comes from. Why is it constant over N cubed? There's just and if you think you have an idea, see if it's coming, I'll talk about it. See what your idea says if there are 4 gamblers. But so constant over n for 2 players, that's true, and constant over n cubed for 3 players. What is it for 4? So let me talk about this problem. So this is a problem of the type we were talking about. Namely, it's the first, hitting the boundary. Where do you hit the boundary? Here are some numbers. I'll explain where they came from. And in fact, okay, so we can get we can get as exact an answer as we want for reasonable values. And so these are double precision numbers, or maybe a little more, for the problem 1, 1, n minus 2. And what's the chance that the big guy is eliminated first when n is 50 and multiplied by n cubed, so you can see them. So there it is, 4.55. When n is 100, it's 4.5597, 150 up to 300, 4.5597945. The right answer is 4.55979 something, 49, not 45. So what we first did was to calculate exactly, in a way that I'm going to explain, these numbers. And when they stabilized, we said, well, they predict that this is the answer, and they stabilize. Of course, that's just a guess from relatively small numbers. But there we were. It's a natural thing to guess that it seems to be constant over n cubed. So here's a little math. So here's some tools. And let me go back to the general setup. That is, the general setup is I have a finite state space and X, and then I have a space B, subset B, and I start at a point X naught, and then I bop around until I exit the space. And what you can do is rearrange the transition matrix. So this is the matrix K of XY, and I've rearranged it so that all of the points outside the B I'll call them the boundary, are together, and then the interior are together. And then the big matrix factors into 4 blocks. There's no chance of going from outside, from a boundary point back inside. You die. So the chance of going from a boundary point back inside is 0. The chance of, if you're at a boundary point, you stay there. It's a cemetery point. And so there's the identity in this corner. There's some chance that you're given, this is a given matrix, that if you're in the interior, that you move to the boundary. For each boundary point, we have the probability K of XY. So that matrix is called S. And the chance that you move from some interior point to some other interior point is Q. So that's a natural parameterization. And an elementary, it really is an undergraduate exercise. I'll explain. I think it's transparent. For X in the interior and Y outside B, for X in the interior and Y in the boundary, the chance, which will be called P of XY, that starting at X, the chain first reaches the boundary at Y, that is the second question I was interested in, is given by this matrix formula. It's the identity minus Q inverse. Q is this square matrix, and so this will have an inverse, and then times this matrix S. And if you think about that, if you just expand 1 over 1 minus Q, that's the summation of Q to the J. And so what this says is the chance that you go from X to a point in the boundary, well, you had to have stayed in the interior for some number of steps, J, and then taken a step from wherever you are to the boundary. So this is transparent. This formula is transparent. this matrix, this P of xy, has various names. It's called the Poisson kernel in analysis. It's called harmonic measure in analysis. And it means the chance that starting from inside, you hit the boundary at y. And now, so in principle, for small n's like 300, you could just compute. And so for Gambler's Ruin, I minus q inverse, that required inverting an n minus 1 choose 2 by n minus 1 choose 2 matrix. And when n was 200, that was 19701 by 19701. And Stew, my co-author in this work, Stew Ethier, did it in Mathematica in double precision. Don't laugh, those of you who know how to compute, but he likes Mathematica, and it took 97 hours to compute that inverse. So my numerical analysis colleague, Lexing Ying, laughed at us and said, that's a sparse matrix, and it's just a vanilla sparse matrix problem. It's still, if you want to do it for real numbers that come up in practice, like the numbers that come up when you want to evaluate probabilities for the World Series of Poker, you can't do it. It's too big to do it by numerical analysis directly. But these formulas are where these numbers came from. Okay, that's where these numbers came from, and so they led us to conjecture that this constant stabilized, and there are many other ways to get numbers, and direct inversion of the matrix is one way, and you can do Jacobi iteration to get upper and lower bounds on the matrix. And in the paper I wrote with Stew Ethier, Gambler's Ruin and the ICM, it's called, and it's a friendly, readable paper. We have 6 different ways of getting numbers. And we compare them and see what their running times are. And this, if you want something very accurate, maybe it costs you more. And there are many different approaches to computing the Poisson kernel or approximating the Poisson kernel. And our paper explained them, invented some new ones, and tried them out in this problem. Now, there's some harder math, and here it comes. For 3K, let's look at special case, 3 players Gambler's Ruin, and this is work drawn from a paper I wrote with Kelsey, Huston-Edwards, and Laurent, Saloff-Coste. So remember, I start at A+B+C, and each time I change by 1, and the total sum n is fixed. A plus B plus C is n. And so we're doing a random walk on the triangle, the set of all triples, where A, B, and C are non-negative, and A plus B plus C sums to n. And so really you just need to track the first 2 coordinates, A and B. And this is what the state space looks like. I can't see my cursor. It's here someplace. There it is. So this is when n is 6, and the set X are these open circles. So this is the set X, this is the interior. The boundary, the outside, is where one of the players is eliminated. This is player C. This is players, B and 2 and 3 have all the money. This is player 1 and 2 have all the money. This is players, however it goes. But the 3 boundaries are the sides of the triangle, and they're not accessible from the inside, but the full problem, one of the players wins all the money. That's these 3 big circles. Okay, so the game is with a bigger matrix. Every point is connected to 6 neighbors, and that's the Markov chain. So it's a 2-dimensional process, in fact, and by symmetry, you only need to know the chance that if you start someplace inside, x1, x2, I'm calling it, what's the chance that you hit, say, this edge at the point, well, funny notation, but at the point y and 0. What's the chance that you hit this edge here, 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 or here? If you know the answers to those questions by symmetry, you know the answers to all the questions. So here's a theorem that the three of us proved, and it's a lot of hard work, but still, well, let me explain the theorem. So the chance that if you start at x1, x2 inside, that you first hit the boundary at y0, I'll explain all the notation, is given by a funny rational function, x1, x2, x1 times x1 plus x2 times n minus x1 minus x2, etc. Here's y coming in, y squared, n minus y squared, and then there's a denominator, n to the fourth, x1 plus d. What's d? I'll tell you in a second. So there's an expression for this Poisson kernel. Now, first of all, what's d? So d is the graph distance from where you, the graph distance from where you start to y0. Okay, so, you know, here and there, for example, or there and there, the graph distance. That's the first thing. The second thing is, what's this double wiggles? And I'm not proud of that, but it's a math talk, so here's what double wiggles are. Double wiggles is defined as upper and lower bounded by fixed positive constants. So I write an double wiggles bn if there exists c and c prime, both positive, such that bn is bounded between those two constants times an. And now what is important is that this theorem is uniform in everything in sight, in n, x1, x2. The c1 and c2 are computable. They're not horrible. You know, they're 6 1/4 or 6 1/4 or something like that. I mean, they're not horrible, but they're it's not wiggles. It's not ordinary asymptotics. But this is the answer for all points and all boundary points. It's a uniform answer. So it's remarkable. Some way you can get the answer. And if you want to look at a hard paper, I recommend it. It's a hard paper. Whitney covers, Carlson estimates, beautiful classical analysis. When you specialize this to the problem that I'm trying to talk about, what's the chance that if two of the gamblers start at 1 and the third one has all the rest of the money, what's the chance that player 3 goes broke first? You can put in those numbers in this approximation, and it gives you that this probability, the thing that we're interested in, is double wiggles is asymptotically equivalent to 1 over n cubed. And of course, there are two constants. So, but that's a theorem at least. So I know that it's not constant over n squared. I know it's not n squared over log n. It's two constants over n cubed. And I'll come back and talk a little bit about that math. We have those kinds of theorems for general domains and not just triangles and gambler's rune, but that's coming. Okay, now what happened was, so I was going around, very pleased that we could prove something, and one of the postdocs at Stanford, a guy named Sanchal Lee, had an idea. So I call this next topic a success story for experimental mathematics, given that that's the title of this seminar. So everybody knows here that whatever Brownian motion is, some particle wiggling around in continuous space, random walk is well approximated by Brownian motion. And that's true in 2 dimensions too. That is, if you have a triangle and if you have Brownian motion started at some point inside the triangle, you can ask, what's the chance that you first hit the boundary? How long does it take? In the continuous time and continuous state space setting. And as the mesh gets fine, or as n gets large, the grid answer in various senses approaches the Brownian motion answer. And one of our postdocs, Sanchal Lee, said the following: the Brownian motion problem we can do because, well, it's Brownian motion on a triangle, but a triangle is conformally equivalent to, there's a conformal mapping that takes the triangle into a disk and takes the starting point, and then you know the Brownian motion on the disk is very well studied, and we know what the Poisson kernel is, and you can translate all of that. And he did a lot of the math and waved his hands. It wasn't all math, but he solved the first hitting time for Brownian motion on a triangle, and he found the magic constant, that ratio of gamma functions and everything. Now, this frowny face is meant to make the following point. We also all know that Brownian motion only approximates random walk to up to, constant over root n, or if you're lucky, if that term cancels, if there's some symmetry, up to constant over n. The error term in the Brownian motion approximation to random walk is, constant over root n generally, and maybe constant over n sometimes, if you're lucky. And we're trying to say something about constant over n cubed. And so, the fact that the Brownian motion problem has a nice answer and the right answer, it didn't help. I mean, we couldn't make good approximations. And so it was a finding of experimental innovative math. And then there was a question, seemed to be true. And so recently, two wonderful probabilists, Denisov and Wachtel, managed to prove it. And they have a machine that they've been building for years about Brownian motion inside of cones. And this problem fit into their machine. And by doing 30 pages of hard work, they were able to prove this constant over n cubed for this C. So I regard that as a success story for experimental math. I mean, experimental math allowed us to guess at the answer, and then somebody got interested and pushed it through and was able to prove it. And it's good to 20 decimal places, and I think it's in good shape. I mean, that's what math is supposed to be doing.
You had an experimental proof before with up to capital N equal 300. So it a waste of time to have a so-called rigorous proof to something you knew for sure.
Oh, the ends that people care about are in the thousands and tens of thousands. And I don't know. I was suspicious, and that's something where now you're bringing religion into it. Are asymptotics useful? Are exact answers the only thing to do? Come on. Let's keep religion out of it. And I'm trying to tell a story. It's a pretty clear story. And I'm glad you want to put your name in. You always do. And I'm glad you're interested, Doran. But I think this is a success story for math, and more is coming from this success story. Okay, what about four gamblers? Okay, so let me refresh our memory. So if you have two gamblers with $1 and n-1, the chance that the big player is eliminated first is small. How small? 1 over n. With three gamblers, what we just said, the chance with, say you start at the corner, we can do it now for pretty generally. Say you start at the corner, 1, 1, and n-2. What's the chance the big player is eliminated first? It was constant over n cubed. So, is there a guess, or what about four players? So,
triangular number.
Neil and I each have $1, and Sam Spiro has n-$3. And what's the chance that Sam gets wiped out first? It's small. And it's smaller than n cubed, but is it n to the 4th, n to the 6th, n to the 17th? Well, it's impossible to guess. And I mean, it's possible to guess, but it's impossible to guess correctly. And here's some progress. first piece of progress is O'Connor and Saloff-Coste, in a paper called Four Players Gambler's Rune, proved that the answer to this problem is double wiggles, but still that just means there are two positive constants, which are computable. It double wiggles 1 over n to a power, but the power is not an integer, and it's not a recognizable number. I mean, it means something. It's an angle in some cone, but so anybody who says, "Oh, I've got good heuristics about where 1 over n cubed comes from," yeah, I don't believe it. So this is a theorem, and their paper is interesting because the numerical analysis is very, very tricky. This blends with a chapter of numerical analysis where numerical analysts realize that some problems are very, very delicate, and this problem is very, very delicate. And to get more decimal places in this number seems beyond us. And to say Denisov and Wachtel, the paper that I cited before, this one, allows you to, probably would allow you to get what the constant is with this power. So there is a Brownian motion problem, which is Brownian motion in a cone, and you stop it when it first hits the sides of the cone. And they know a lot about that. And now they've built a machine to allow some kind of transference. And so those were special cases of our big problem that we started with. We have a Markov chain. We stop it when it gets outside of some fixed set. How long does it take? And when it gets out, how long? Where does it hit? Here's a present for the audience, I hope. So these are, all of these problems are a paragraph with references, and I'm not going to say them now. All of these problems are a paragraph in my paper with Stew Ethier. So Gambler's Rune in the ICM, it was called. These are open problems with K gamblers, and I think that they're clean and nice and definitely worth solving. So here's the first. So I've been doing, they all start this way. You have K gamblers, and they have, A1 up to AK dollars. And each time you pick a pair of gamblers, and then they're going to play, and something happens between them, okay? And the thing that I'm going to change is, instead of flipping a fair coin and you go this way or that way with probability a half each, maybe make, if it's real poker, for example, usually in poker hand, more than one unit gets exchanged. So here's one variant, and we called it all in. If the two players that are chosen, all of the variants start the same, pick two players at random. If they have A and B, you make a bet of a large amount, the minimum of A and B, the biggest possible bet you can, and then you flip a fair coin, and then if it comes up heads, one player gets min AB and the other loses min AB. So what that means is that the player with the smaller chip count is eliminated or doubles up, and then the game continues. That's a pretty natural version. That is, think of monsters with big piles of chips in front of them playing poker. When hands are pretty big, usually when the money starts to go in, it gets down to two players. And which two players it is, that has to do with the cards that are dealt. And so it's not such a bad assumption that on the big hands, it's two players chosen at random. And then, if it's not such a strange thing to say that one taps the other, and so all the money goes in, and whoever has the biggest hand wins. So it's more realistic poker-wise than the variant that I was talking about. And as far as I know, nothing is known about it. So now it's not such a local Markov chain, but it's a Markov chain. It's a clear, natural, simple problem. And I hope somebody thinks about it and let me know if you make progress. So that's my first suggestion, all in. The second suggestion is maybe a little more natural, and you can easily see how to vary it, but this is a clean way. I'll call it occasionally all in. That is, so two players are picked uniformly among all K choose two players, and if they have A and B dollars, then an amount, there's a fair coin flip, but an amount is transferred and it's uniformly chosen between 0 and the largest it could be, namely the minimum of A and B. You could put a different distribution there, but uniform is perfectly reasonable. So the bet is something in between the most it could be and $1, and that's maybe a little more realistic. Anyway, it's a clean, nice problem. The nothing known as far as I know. I mean, any of our questions, and at least by simulation one could study, or recursion, or whatever you like. This one has a little literature. David Aldous was selling it about 20 years ago, and it's called The Compulsive Gamblers. So again, K gamblers, two picked at random. If they have, one has A and the other has B, then they transfer money by gambler's rune. That is not one at a time, but with two players, one gets the other's money with probability A over A plus B or B over A plus B. That is the usual probabilities for one player or another winning all the cash with gambler's rune. So they play until death. I mean, takes one of them, and then the game continues. So this problem has, if you look in our paper, there's a paper of Aldous, I think Celez, and third guy, wonderful Brazilian probabilist, Hubert. Anybody want to help? Hubert, that's his first name. Anyway. So there's a little bit of literature, but the kind of problem that I'm talking about is open. So that's my effort to help somebody out there. That is, those are three nice problems, and nothing is known about them, and I think they're all interesting. Let me go back in the few minutes remaining, because Doran is a devil about the time, and good for him. Back to the general setup. So I started with this general setup. I started with a state space X, and a Markov chain KXY, a transition matrix, and a subset B. And B, this is work with Laurent Saloff-Coste, who likes pathological things. I mean, B could have holes in it. It could be anything. B could be any horrible thing. And one of the basic theorems of Markov chain theory, a little less known, but still, certainly at the undergraduate level, is the notion of a quasi-stationary distribution. And let me first say it in words and then say it in symbols. So suppose I have an absorbing Markov chain, as I do. That is, this chain wiggles around, and when it gets outside of B, it stops. Okay. The quasi-stationary distribution is this. Suppose the chain has been run for a long time and it hasn't been absorbed. Where is it likely to be? Okay. So as math, it's a theorem that if the original chain is ergodic and B is connected under minimal assumptions, look at the limit of the probability that this should have an X naught on it, limit of the probability that at time t, for large t, that at time t, the chain is at X, given that it hasn't been absorbed up to time t, given that it's still inside of B. And that limit exists, and it's called the quasi-stationary distribution. And it has a very, you can say what it is and you can compute it in small examples. But let's just think about it in a simple special case. Suppose I have ordinary gambler's rune. I start someplace at X naught, and I stop if I hit 0 or hit N. And the thing's been going a long time, and it hasn't stopped. Where's it likely to be? Well, it's not so intuitive, but when you hear the answer, it's maybe more intuitive. It's likely to be in the middle. And the stationary distribution, the quasi-stationary distribution, is like a piece of cosine, symmetric about the middle. So it's most likely to be in the middle, and then it falls off, and there's a formula for it. So that's called the quasi-stationary distribution. And it's a question which in general is hard. It's hard numerically, it's hard mathematically. In natural problems, what is the quasi-stationary distribution? Find a formula or an approximation for it. This is a limit theorem problem. There is a limit. Can you describe it? Can you compute it? Can you work with it? Now, I have spent much of my career on non-absorbing chains that keep going forever. How long do you have to shuffle a deck of cards to mix it up? And a few years ago, it hit me out of like a bolt from the blue. Wait a second, there are absorbing Markov chains. We all die. You stop when you hit the boundary. You can ask the question, what about rates of convergence to quasi-stationarity? Suppose the chain has been going for a long time. This is a limit theorem, right? So what are the asymptotics in this limit theorem? This approximate this. Take the total variation distance between these two measures or any other distance and try to get your hands on it. That's another set of questions about absorbing Markov chains in general, and of course for Gambler's Rune in particular. And I wrote a long paper, long as in 120-page paper, with Kelsey, Huston-Edwards, and Laurent Saloff-Coste, which is called Analytic Geometric Methods for Finite Markov Chains with Applications to Quasi-Stationarity. And it's published in an online journal called Aliyah. And it's on my homepage, and it's on the archive, and it's soon to be a major motion picture. So recapping, this was a talk about natural math problems about absorbing Markov chains, and I try to tell you there are natural ones. There are lots and lots in biology, in computer science applications. There are lots and lots of times in which it's a natural thing. You want to know how long does it take until the job is done, until the process hits the boundary. Where does it hit the boundary, and how does that depend on where it started? And then if it hasn't hit the boundary, where is it likely to be? Those are natural questions in some generality, and I illustrated them with hard work in a very special case, the case of three gamblers, and I find them interesting problems, and I hope you do too. So I think that I'm supposed to stop and stop my share and wave hello. Hi, Chip, you came back. Oh, that's good.
There's plenty of time for questions from the audience.
Or complaints are okay too.
I have a complaint. You were bragging about how long the papers, very long papers. So it is worth the trouble of writing such long papers?
Well, that's a funny thing. So I like writing papers that human beings can read, in particular me. And I have had papers sent back from journals saying, this paper is well written, but it's written in such a way that a graduate student could read it. Please reduce by a third. Well, that's a crime. It's terrible that people say that people won't let you write papers that other people can read, that only specialists can read. And we've all had that problem. So if you look at the paper we wrote by the way, if you don't know who Kelsey is, Kelsey Huston-Edwards, she's much more famous than Laurent and I will ever be put together. She had an online, she's a PhD from Cornell, but she had an online, unbelievably popular program on math for everyone, understanding things. And she's now writing for Scientific American. She got her PhD, but she likes explaining things to people. And so the paper's just filled with pictures and you can actually read it. And then it's got a lot of stuff in it. And in this particular case, this paper used tools that are completely foreign in probability. Carlson estimates, Whitney domains, inner regular domains, techniques that are borrowed from, cutting edge PDE that probabilists just don't know. And so we try to explain them. I don't know, it seems like a good thing to do. If you don't want to learn it, you don't have to read. It's online too, right? So you don't have to read it, but you could read it if you wanted to. And,
but if you have a general mathematical background, you can understand it. You don't need any specialized knowledge to read it cover to cover.
I know you don't need. I think any graduate student in mathematics or in statistics could read it. So now, okay. So could my wife's mom read it? Probably not. But I mean, she doesn't know what a derivative is. So okay.
Persi, can I ask you a question?
Yes.
You had a nice sequence that began 1, 3, and I was sure it was going to be 6 next, but it's close. It's 5.65 or something. But do you have the next term?
I don't have the next term.
Five player gamblers.
I don't. I mean, do I have the next term?
It's going to be near 10, right? It's going to be close to 10.
Oh, you mean for 5 gamblers? Probably that is. I don't know, Neil. But the place that I would look is in Saloff-Coste's paper on Gambler's Ruin with 4 gamblers. He probably says what their best guess is. We could get approximations to it because I could do it when n is 100 or something like that. I mean, I could do it out by inverting the matrix. And maybe Denisov and Wachtel have it, but I don't know what it is.
Okay.
The number for 4 defeated people for quite a while. So it was, the other thing that's funny is there are all kinds of people who pretend they know things. And I've had people, make, surely, 1, 3, 1 over n cubed. The next one will be, when they say it with a sage nod at you. Well, pardon me, but BS, math is math. It's why we compute things. It's why we prove theorems. So I had some Fields Medal winners do that to me, and it was a pleasure to say, you don't know what you're talking about. So I don't know, but we could find out. I think that they know a few decimal places of the next number, but
yeah.
But if you do it numerically for n equals 3, how close can you estimate the 1 over n cubed? That numerically.
Well, but I showed those numbers. I got them to 20 decimal places.
Yeah, so it's pretty convincing. So probably same thing with 5 players and get a rough, at least some estimate.
It would be, those. Yes, maybe you could use some of the sparse matrix techniques, but you'd have to be very serious about it. So if you were interested in 5 players, the matrix that you're inverting, even if it's sparse, would be something like, n to the 5th by n to the 5th, right? Well, pretty soon we're talking big numbers. And no, but I mean, it's 2023 and parallel and sparse matrix. I mean, but you'd have to be serious about it. And as many of you know, I'm a guy who hardly does email, right? So the idea of me trying to compute any numbers, but they're rational numbers, actually. I mean, they're in our paper. They're rational numbers.
So see, if email doesn't work, What's the best way? Write you a letter, right?
Oh, no. So I did not do email for a very long time, but I got caught in Zoom and I had to teach online. And Susan was in Portugal and I was here. And if you want to laugh, there I was with a computer, an iPad, and my phone, holding it up and her screaming at me, "No, don't push that button." I did learn to teach on Zoom. I gave this talk. I hope it was satisfactory. And so you can email diaconis@math.stanford.edu and I'll get it. So diaconis@math.stanford.edu will get it. And I'd love to hear from you and say hello to Susanna.
I will indeed. Thank you. And thank you for introducing us 45 years ago.
Wow. We have known each other a long time, but that was a success. Great.
You need some sequences for Neil. So when you do smaller and you get some rational numbers with numerator and denominator, so maybe you can get some.
Neil has enough sequences.
Persi, let me just say that was a wonderful talk. Thank you.
Thank you. I'm glad it went okay. Well, giving a talk to your friends, that's got to be one of life's pleasures, right? So
yes, wonderful.
I thank Doran and thank all of you. Thank you.
One time for quick question from the other members of the audience.
Somebody ask. Sam, come on.
Hi, I have a question. Hi, so can you say a few words about the scaling conjecture? Because
yes,
it's a very nice one. Exciting.
No fair. You looked at my paper. No, bless you. Bless you. So one of the things that all gamblers know is that if you want to compute the first hitting time or things about ABC, if you double or triple ABC, everything should scale up in a natural way. And so it's just a very natural, the chance that we go, 1, n-2, that the big guy wins should be the same as the chance if we go 3 times n-2. And so that sounds right. Everybody behaves that way. And it's right in the limit. Brownian motion, the Brownian motion limit rescales exactly that way, but it's false for small n, but it's false in the 4th or 5th decimal place. So it's close to true. And trying to make a theorem out of that is a problem. Thank you. It's a wonderful question. I should have put it in. We did a lot of computing about how things change when you just, multiply all of the numbers by a constant. And we have, specific conjectures that it only changes in the 4th decimal place or something like that. But I can't prove anything. So,
so you're actually saying it's not true, right?
Oh, it's not true exactly.
It's not true exactly. Oh, wow.
Not true exactly. Because that you can see when n is 6 or something like that, and then double it. We can compute exactly. We give numbers in the paper to show that, it differs in the 4th decimal place or something like that.
Because on the other hand, you mentioned in the paper that for k greater than 3, you have evidence it's also true.
Yes, we think it's true for all k.
But still with a small error. I see.
Yeah.
Okay.
And maybe the error depends on k too.
Okay.
So it's a nice natural conjecture. Giving a quantitative version. If n is sufficiently large, there's a theorem to be proved there. You try it numerically, it's true. And so maybe now that Denisov and Wachtel have proved this thing, their proof is more general than what I said. Maybe you could look at their argument and get out some quantitative version of the scaling conjecture as a theorem, because it's true for the limit. The Brownian motion scales perfectly, and then if the limit approximates the random walk, for certain problems, then maybe now. It's a couple of years after our paper, that would be a way to proceed. And their paper is very beautiful math. it's surprising how deep it is. It's just Brownian motion in the cone, and what's the first time you hit the cone, and when you hit it, what face do you hit it in? And it's just great math. It's hard and it's beautiful. So I recommend their paper. So, and then maybe there's some transference. What's your name? I don't know. Who are you?
I'm a postdoc here.
That's okay.
Yeah.
What's your name?
I'm Stoyan.
Again, right before you talk in the Zoom
In Haifa. Yeah.
Good. Hi, Stoyan. Nice to meet you.
Yeah.
Come, I'm going to give a talk at Rutgers at Tiep's birthday next week. Come say hello.
Oh, wow.
Well, it's
time to go.
No, it's at Princeton. Sorry, it's at Princeton. Sorry. But it's not so far.
Well, it's a good time to stop. Thanks so much, everyone, for coming. And Persi, thanks for a great talk. And please email me the slides, even though you're not good at email, so I can post it.
I'll send them right now. Bye to everybody. Bye-bye.
The recording will be available next week, and we'll let you know as soon. Thanks so much, everybody, especially for Persi, for coming. And this ends this talk. Robert, please terminate this.